obviously not right, but we'll go ahead and get started here. We're going to pick up with session 7 here, and this will look at the climatology of supercell tornado parameters. We've already looked at the parameter development itself. That was back in session 4. And so we've sort of set an ingredients-based approach to forecasting supercells and tornadoes. So the point here is that we're going to look at how do these ingredients vary. You hear it all the time where people talk about, well, you know, we don't get storms like you guys get or that sort of thing. It's really they don't get environments that like you guys get, that sort of thing. So just to remind everyone where we are, again, session 7, we will hit numerical models. I'll talk about that stuff in some detail next week, and then hopefully if the atmosphere cooperates, we'll do some kind of real-time forecast exercise. However, we're going to break from the standard approach. I figured they'll be interested in tomorrow since everything lines up. So we're going to sort of take a pseudo forecast look at tomorrow based on what I put together early this afternoon. So this is one where kind of a sneak preview of what we'll do here in 2 weeks. So what I want to do is take you through some of the information I'd look at. Again, this is going to be abbreviated because it's tacked on to the session, so I don't want to drag this on too long. We'll go over it in excruciating detail in 2 weeks if everything works out. All right, we have a system coming up. Obviously, a few people, there's probably a few out wandering around right now. Have any storms formed yet? Last I checked, there were no storms. Okay, chalk one up for the forecasters. And in this case, we have a deep mid-level trough over California, and this was as of 9Z this morning, so I'm going to show a series of water vapor images. These are 3 hours apart, and what I want to do is highlight some of the things that could come into play tomorrow. So we have the large-scale wave. It looks like, you know, if you think back to the session 1 QG theory type stuff, you know, in this case, it's relatively zonal flow, vorticity convection downstream from the trough. This should move largely east. That's as it's forecast. However, you notice I have some arrows highlighting a few smaller scale features in there. This is the kind of stuff you have to worry about when you're doing a forecast, and a lot of people gloss over these details, especially when you're talking a day or two in advance. Every one of these little speed maxima, these little waves, has some potential to be associated with deep convection. If you look in Missouri, you see a cluster of storms that have formed overnight. There's a little speed max that the storm cluster immediately precedes. Another little subtle one coming out into western Oklahoma. We'll see if that has any influence in southeast Kansas tonight. And look way off to the lower left. There's another little one. Where do you think that's going to be? About 21 to 0Z tomorrow. That's going to be sitting out over near the Kansas-Oklahoma border as a rough guess. Point is, what's going to happen in response to that? Will it have any influence in the low levels, or could we have some deep convective response? Got to consider these things. It's not as simple as there's a big trough coming and there will be tornadoes. I hope that it's clear that it's not that simple at this point. All right, we'll look at some of the soundings from this morning.
Quick question. If you go back to the water vapor imagery, how are you identifying all of the different speed maxes? Is it based upon the vorticity contours that you have there, or is it just the drying versus the moistening?
For those who couldn't hear the question is how did I identify the speed maxima in water vapor? Am I using the vorticity isopleths? Am I using something about the image itself? It's actually, the answer is yes, it's both of them. So in this case, if we look back, primarily if you follow the areas of darkening, that usually represents some form. There's brightening downstream, which is related to mid-level moistening, subsidence, and darkening from upstream. So it's air that has a history of subsidence. You can usually track these vertical motion couplets. So the dark areas are usually the easiest to track because they're not associated with clouds. You know, the clouds can form and whiz off somewhere further downstream a little quicker. So remember, the waves move slower than the flow. The flow is moving through the wave, but in this case, if you see the cirrus, which the thunderstorm anvils are very bright, that stuff can that'll move with the flow. So they're not as good a tracer. So we tend to trace the dark areas. It just depends on the enhancement you're using. So in this case, if you watch those, you just kind of step back. You see these little dark streaks with some continuity. And again, that's about a 9 to 12 hour loop. So the idea is you have to look for these things, and a lot of times you can't see them until the day of an event. You know, 2-3 days out, you're thinking, oh, this is going to be great. And then you come to day one, like, wait a minute, where did all this mess come from? And it's these smaller scale features. You're welcome. Okay, so we'll look at some of the soundings. We talked about, the large scale, so we want a source for ascent. We'd like to see cyclogenesis. We have a large scale wave approaching. We do have some complicating factors, as we pointed out. We also want to decide in terms of our ingredients. Just think back to the first couple of sessions. We're looking for lapse rates and moisture. Well, the Topeka sounding, and you'll see all these soundings up and down the plains. The elevated mixed layer plume is very pronounced as of right now. That's part of the reason that there may be some folks still kind of loitering near the Kansas-Oklahoma border without storms because we had a very warm elevated mixed layer and it's not strongly forced today. Steep lapse rates, nearly dry adiabatic in the mid-levels. If you follow this back like we did in our exercise, this is the mixed layer that was sitting out over Denver, Albuquerque, and the plateau yesterday. Moisture sitting beneath that. You continue down to Norman, you see the same elevated mixed layer. We continue down to Fort Worth. Now you notice as we go south what's happening to the moisture profile. It's not getting deeper. In this case, the moist layer does not extend quite as deep as 850 millibars. Now, when we talked about sources for lift, we mentioned the dry line circulation yesterday and today. That's been relevant. In this case, if you recall, the peak vertical velocities on the dry line are typically scaled to about the height of the moist layer depth. Well, that's pretty shallow for profiles like this. Now, it may get a little deeper with mixing during the day, but it's pretty shallow compared to the LFC, which is up around 700 millibars. So the point here is when a shallow moist layer says something about the vertical motion profile on the dry line. And notice where the steep lapse rates and dry air are, trajectories are coming out of the west. So it's westerly flow. That's not from a moisture source. So the point is, and if you remember residence time in that dry line circulation, in this case, it's not very long. The parcels ascend, and then they immediately detrain. They end up going off to the east over the moist air, and they never reach an LFC. And then we continue down to Corpus Christi. The dew point at the surface is fine, 68 to 70, but the moist layer itself is relatively shallow. So this is a case where you might have questions about what's the quality of the moisture going to look like tomorrow. Is it going to get better? Based on this information, maybe not. It looks like what we have is what we're going to have tomorrow. Okay, so I'm going to switch and we'll look at precipitable water. This is derived from satellite imagery and it's sort of got a model first guess basis in the background. The colors going from the blues to the greens to the yellows and reds, that's getting moisture. The reds are 1.5 to 2 inch precipitable water. The one thing I want to focus on is look just off the Texas coast. You notice that green area, that's actually lower precipitable water. It's reflective of the shallow moist layer. This goes back to 9Z, 12Z, 15, 18. Same features still out there. Other than where there's clouds in the Gulf that sometimes contaminate this, it's not particularly moist through a deep layer. So the skin layer looks fine, but the boundary layer itself isn't that deep. So this is a case where there's no more air mass modification going on. It's already warm and moist at the surface, but the layer's not very deep. So what happens to that when it comes inland? You're subjected to heating and mixing. The moisture doesn't increase. And I did just to show this was a surface map I scribbled out at 19Z this afternoon on shift. And I've just highlighted the 64, 68, and 72 dew points. And if you look real close on the Texas coast, there's a 72 dew point contour that essentially mirrors the coastline. And then it quickly drops to 68 as you move just a county inland. That's the impact of the vertical mixing. It gets warmer as soon as you get inland from the coast. And that shallow marine layer is actually being redistributed from a higher dew point in a shallow layer to a little bit lower dew point through a deeper layer. And that's why you see this sort of pattern. And there's perhaps some enhancement up in Oklahoma with a little patch of upper 60s, which the Mesonet verifies. Those aren't just AWOS observations. So they appear to be real, but it could be an evapotranspiration response. We are greening up, especially south of here. The soil's moist. Again, we'll see what the sounding looks like this evening. I obviously don't have the luxury of looking at that yet since it's not even out. So again, keep in mind we got lapse rates, we have moisture, some concerns about depth, and we also have little preceding speed maxima, which could be complicating factors sometime during the afternoon. Okay, so I've said all along I was going to try to stay away from the model stuff. I have to cheat and use a little bit of it here. I really want to focus on it next week. So I'm not going to show you too much good stuff. This is just going to be basic fields. We just want to look at what the evolution of the forecast is for the broader synoptic system and then get you thinking about how that might play out. Okay, this is a forecast of outlet at 12Z in the morning from the 12Z NAM So it looked pretty similar to the European model, it looked pretty similar to the GFS. There's pretty good agreement in the synoptic regime, as you might expect as the wave is being sampled as it moves inland on the west coast. So we step through this, and you see during the day, the synoptic wave is back over the Rockies, but we have this other belt of flow. That is some representation of those little squiggles that you see in water vapor, which is part of that layer, because water vapor imagery is sensitive to roughly the 700 to 400 millibar layer. So you don't see down low, and you're not really looking way up high. So in this case, there are other little features, little speed maxes involved, embedded in that flow little stream, so that's something that might be related to subtle changes in the ascent fields tomorrow during the day. Now, what else would you expect? Waves approaching southeast Colorado. Where's the highest terrain in the Rockies? It's pretty close to there. Where's the favorite lee cyclogenesis location? Probably in the world. It's southeast Colorado. So you would expect, with increasing flow over the Rockies, lee cyclogenesis, we should see some low deepen in place, just based on the synoptic regime. And we'll take a look at the forecast. And then tomorrow night, the wave finally starts to emerge over the high plains. Okay, this is the response, mass response in the low levels to the cyclogenesis. Here's the morning with 850. The color-filled area is 30 knots or greater in blue. So we have a southerly belt of flow, 30, 35 knots. Not particularly strong during the day, stays about the same. Some increase in the evening. Now again, you notice we see the heights fall down towards southeast and east central Colorado, and we talked about the low-level jet and the nocturnal response. This is a case where you might see something like that. And indeed, the forecast shows from 0 to 6Z, there's a rapid increase. Those are 50-knot winds in there. So this is a case where the synoptic wave's a little late. We have these little preceding speed maxima. We have some evidence of a cap, modest low-level moisture for the time of year. It's not bad, but it's not the richest moisture you'll ever see, and a late low-level shear response. So the thing that should be starting to come together in all this is we don't have a scenario that's going to favor like a squall line or anything like that, not initially, because it's not strongly forced. It's a dry line. It's oriented very much across the flow and the shear vectors based on the convective mode stuff. But there's a late mass response. So this is probably going to be a late show, whatever happens, especially in terms of any tornado threat, pending nothing getting messed up mid to late afternoon by one of the early speed maxima coming across. All right, here's the NAM forecast 2-meter temperature and dew point. The light greens down there on the Gulf Coast, that's upper 60s, and then the 60 dew point's the dark green. So those are every 4 Fahrenheit, low 70s in yellow. So we just look, again, the NAM forecast, not too different. I don't know if we could argue that perhaps it's a little on the moist side with the upper 68 to 72 dew points piling up there in the frontal zone. You can make an argument that something like that could happen if it's convergent and we deepen the moist layer locally. That can happen because it's actually sheltered from mixing when you do that. Locally, your moist layer is deeper, so the vertical mixing doesn't extend above the moist layer. I'm not totally sure that's what the NAM's doing because it's been running a little warm on the dew points anyway. And you notice our low just deepens in place. It sits out there in the high plains. The dry line mixes just a little bit east. So a lot of chatter about the triple point. It's kind of demarcated there with the boundary intersection, south central Kansas. So we have a scenario where it looks like in the low levels there's a fairly obvious focus. And the question is, will we get the subtleties aloft to line up with this? And then overnight, the synoptic wave starts to emerge from the high plains. That's going to become the primary cyclone tomorrow, the following day toward the Midwest. All right, I'll throw in some more familiar graphics. This is the kind of stuff you could dig up. I've been showing SPC stuff to this point. This is just the forecast, just to keep in mind right now, and it's very convenient that there's no storms. Are there still no storms? Okay, good. This is the forecast, ML, CAPE, and SYN from the COD site, valid at 0Z. I see 5,000 CAPE based on the unmodified NAM, and I see no SYN. That equals storms, right? I mean, it's that simple, right? No, the idea is when we talked about ascent, you still need sources for lift. You still have to have something going on. Whether it's super adiabatic contact layers near the ground, something to initiate thermals, which is that going to be happening at 0Z? No, the boundary there is going to start to collapse. The heating, peak heating was way back early afternoon. It's not now. So the idea is we need the boundary. Now we do have that front sitting there. I think eventually storms will form, but it's not as simple as, oh, well, it's uncapped, we'll automatically have storms. Because if you just looked at this graphic, you'd say, oh, well, this is a sure bet before sunset. And then now the sun's about to set and you're still out there. But it's a sure bet. I mean, again, it's what I'm trying to emphasize with a lot of this is it's never, ever simple. There's always a complicating factor. And when it works, because you use some real simple logic, you're just lucky. That's all there is to it. You just got lucky. All right, so here's the forecast for tomorrow. Let's see what it looks like then, keeping in mind what is happening today and what it looked like. So the CAPE's in forecast, 12Z, 18Z, still shows some inhibition, moderately strong instability, and then there we go by 0Z, it shows weaker inhibition up toward the Kansas-Oklahoma border. Actually, the CAPE has come down if you look at from 18 to 0. Now, some of this, just keep in mind, why would the CAPE go down from 18 to 0Z? Think complicating factors, what other things that might be going on. But it does look like it's relatively weak inhibition up in the area close to the triple point, so we at least have a focus, and that looks like it might be the most favorable thermodynamic profile. Again, this is taking the NAM at face value, which may or may not be a good idea. So just keep that in mind. So here's the NAM forecast for precip. It actually looks like it might not be too far off. That's the valid 18 to 0Z, the 6-hour convective precip. I don't see anything. And if there's still no storms, all it's got to do is hang on for another 17 minutes and it's right, which it's one of the few models that was dry that long. But we go in the morning, eventually overnight, even the NAM has some convective response into southeast Kansas, and that's another factor that we'd have to consider is how does any overnight convection evolve? Because I'll show you when I show one of the convection allowing solutions that may come into play. Okay, now I mentioned complicating factors. Here's the BMJ scheme. We'll talk about this more next week. There's light convective precip all across west central and northern Oklahoma, 18Z. This is some response to one of the lead speed maxima. The question is, it's not widespread convective overturning, but it does change the radiation schemes in the model. It does change the buoyancy profiles a little bit. Again, the NAM, the scheme, when I talk about it, it's not a standard, it doesn't work the way most of you probably think it works. This one, it's real sensitive to mid-level moistening, not low-level convergence or something like that. The Kane-Fritsch scheme is one of those that's intuitive. The Betz-Miller scheme is actually a different approach to the convective problem. So keep in mind there's a convective signal and this is impacting the buoyancy fields. Now we go to 0Z, we don't see much down the dry line in Oklahoma. That could be true. Our moist layer is a little shallow. It's not strongly forced. Could be the right solution, or is it because we had that light precipitation and its influence on the buoyancy? Because remember, the CAPE actually went down. So it could be some response to this. If you want to get this forecast right, you have to know how those details are going to play out. So if you don't know that, the list of complicating factors is starting to rise. But overall, we do have a favorable pattern for severe storms. Okay, looking at, all I did was grab the 4-kilometer NAM, and because it comes out pretty quick. Let's look at quickly what this one does. This was the forecast value at 0Z. It shows convective initiation, north central Oklahoma. I know there's cumulus there. I don't know if, so it may not be too far off, but if we step forward and look at what it does, it develops a cluster of storms. And this is a little south of some of the other forecasts, and watch how it evolves. We create a little MCS-like feature. Well, what does that have with it? It has a cold pool, outflow boundary. So that's going to redistribute the moisture and the heat in the low levels. It weakens during the day, and then we go to 0Z, and I skipped some of the intermediate ones, and we had storms, a few of them actually form further south in Oklahoma as you went every few hours. So the point is we do have, on the convection allowing scale, a solution that looks reasonable. It fits the synoptic pattern. The question is how much development do you have farther south? Will there be any mesoscale enhancement related to overnight convection? Those are things that you're not really going to be able to say anything definitive about. You can just mention the possibilities. So it's not something you can just absolutely know. All right, let's look at the environment. I know, because I figured I'll just throw the SIGTOR parameter or something in here, because I know people are looking at it, because that's all I ever see on the Facebook feeds, this kind of stuff. So we'll talk about it. And we've talked about all the ingredients, so we're okay doing this. This is what it was forecast to be in the morning. You don't see too much of a signal because the inhibition's too large, the way they mask it, based on the way COD has that. So I forget what the convective inhibition mask is, but once it's too high, it just blots it out. Okay, so we look at 18Z. There's some signal there in southeast Kansas. I haven't looked at the details of what's driving that. And then continue to 0Z, we start to see some sort of focus toward the triple point in south central Kansas. So that's kind of what you would expect synoptically. We start getting a low-level mass response, the low-level shear, the deep shear increase, and the buoyancy is maintained, and the inhibition comes down. So we have everything kind of trying to go in the right direction at the same time if we don't get any complicating convection during the afternoon to the south. Now I'll show you just what the way I look at this same field at SPC. The COD version is a sort of a best guess at the significant tornado parameter using the pre-computed information they have with the model grids. We do it here literally using the same code as the mesoanalysis stuff. So it's run on the supercomputer. We're doing it, calculate, this is the effective layer SIG-TOR parameter. So there's a little stronger signal with it, and that's 4 or 5 there up toward Wichita. So that's into the significant tornado range, and we're gonna talk some more about this stuff later tonight. So again, we've got what would look like a tornado threat. It looks pretty focused. For some of you, it won't be me because I have to work, but some of you that could mean chaser convergence problems, but because it looks like it's pretty obvious where someone might want to hang out. And then we'll take one more look at last little bit of the real-time weather before we go launch into this evening's topic. Look at a couple of forecast soundings during the afternoon and evening. And again, this is, you guys have access to the Python version of Sharpie if you choose to run it. You know, I'll keep giving plugs for that. This is the actual real in Sharp, but it looks pretty similar. This is a case where I've overlaid 2 soundings, the NAM and the GFS, just to give you an idea what kind of variability there might be with the 12Z runs. And the sounding in the foreground is the GFS, the background's the NAM, and I'll toggle between them. This is valid near Winfield, Kansas. So it's a little bit east of Wichita because the GFS had the dry air just east of Wichita, so it wasn't really a representative sounding. But the NAM, so I tried to pick something where they were both in the same relative location synoptically. So if you just kind of look at these soundings, the NAM's a little moister, the GFS is a little slightly deeper mixing, a little bit drier, and it's dry in a relative sense. They both have similar vertical shear, which is in the range of supercells, but notice the hodograph doesn't have a lot of structure. It's a relatively straight hodograph. Again, we haven't had the mass response this early in the afternoon. So this is not what you would necessarily call a super favorable tornado environment just yet. Now let's look down the dry line. This is here, we're sitting east of the dry line here. You know, we have to do Norman since that's where everybody's hanging out here. This a little bit more CAPE. This is 21Z, and this is the forecast. I guess on this one is actually the NAM in the foreground, and then the background's the GFS sounding. So you can see the difference between these two. The differences are, again, they're mostly how deep is the mix layer and what's the distribution of moisture look like, but they're actually both capped. And a little bit different wind profile compared to, a little bit more of a difference compared to up north. But again, there's a lot of interesting structure in the hodograph. You notice that backwards S shape and the winds, it's that subtle backing of the winds with height way up in the mid-troposphere. That's a reflection of one of those lead speed maxima. So there's something coming out aloft that's changing the wind profile. And perhaps some of the mid-level moistenings related to that. But again, the convective scheme is not active in either of these soundings at this point. And then we jump back up to Winfield, Kansas. So this is 0Z, this is just east of the triple point. This is kind of your profile late in the diurnal cycle. So in this case, we've got the GFS in the foreground, and then we'll just switch, and there's the NAM. The NAM's a little bit more moist. Certainly it's cooler because it had more convection up there. They both show increasing low-level shear. The parameter space is improving, and in this case, with the NAM, because it's got relatively high dew points, there's a whole bunch of SIG-TOR analogs that start showing up. So I can't read all of them here, but that's at least a half dozen of them. So in this case, that's the kind of thing you'd want to see. You notice also the yellow in the little SARS inset. Those are significant hail. So there's big hail and some damaging tornadoes come up as loose matches to this kind of forecast profile. Again, it's the GFS, not quite as high on the significant tornado side. Again, its temperature dew point spreads are a little greater. That might be something, because remember, if we want to get heat and mix deep enough to make sure we remove the inhibition, you have to kind of keep the dew points in mind with how warm do the temperatures have to get. Does anyone know how warm we needed to get today, like roughly based on the Norman sounding, to mix through the low-level inversion? I hear it was around 90, something like that. Well, if you throw 90 in, even if you maintain the surface dew points, what are our temperature dew point spreads? They're 25 to 30 degrees, at least 25. That's getting on the high side. That corresponds to an LCL height starting to creep up toward 2,000 meters for an ML parcel. So you can't just add a lot of heat to this and say that'll fix it. You could end up with just high base storms. So there's a lot of subtleties here, but I'd say for a day 2 forecast, this is probably average to slightly better than average confidence. It's relatively predictable regime, and the real question is maybe the inhibition that we have will actually help tone down any convective response prior to the late afternoon and evening storms going up. So, and then we'll jump in, and I see that in this case, this is what we had as the day 2 outlook. I don't have any major qualms with this. I haven't focused too much on the eastern part of it. We have an enhanced risk, which in probability space, it's a 30 sig. I can only speculate what will be done tonight at 6Z. If they stay with this reasoning, it's probably high. I don't think it'll be a 5 tornado. It's probably going to be a little bit higher than that. Maybe a significant area, probably a sig hail area too. So it's hard to say. I've heard mention of moderate risk and that sort of thing. It's just pointless to try to guess what the forecast group that's going to spend the whole evening looking at it's going to come up with. But the point is, it's not just a completely run-of-the-mill day. So there's some important severe weather potential. Seems to be focused near the triple point, and in general, I agree with that forecast right now. So any comments, questions while you got me on this? Because we're going to get away from real-time weather. I threw this together as best I could while monitoring Kentucky and Illinois and wherever else off to the east. So it was a little bit challenging to do that during the day shift. So again, this is a small taste of what we're going to do 2 weeks from now. So we're going to go in some more detail and look at, and I'll go over more of the numerical model tools and how we use that, some statistical stuff. There'll be a lot more background information that I'll bring in next week.
It looks like the moisture depth on the 0Z sounding is a little bit deeper than the 12Z was showing earlier.
Okay, so the comments that the moist layer looks deeper. Now, deeper where? Okay, so Corpus looks a little bit better. Well, then, see, there you go. And that's the point. You look at the observations, because if you rely on a model forecast, especially a couple of days out, you better hope it gets everything right every single day. The mixing profile is correct, the trajectories are right, the underlying interaction with the land or ocean surface. That's a lot of complexity in there. So always check this stuff against the observations. So again, keep this in mind as because I know you guys are going to look at this stuff as soon as I shut up. Just keep in mind the general idea and see if you can sort of fine-tune your guess as to what will happen. All right, now's the regular session. That was all bonus junk that just because we happen to have a severe weather threat tomorrow. So I hope we don't run late, or are you guys okay with no break tonight? You think you can tolerate me for straight through? Okay, well, if someone starts falling over, we'll take a break. But okay, tornadoes by convective mode. What I want to do is I want to share some development of a big database that we worked on at SPC. This is mostly myself and Brian Smith, one of the other meso outlook forecasters at SPC. We put a whole bunch of effort into trying to catalog a good fraction of the tornadoes, significant hail, and significant wind associated with severe storms over roughly a 10-year period. So in this case, I'm going to show you the tornado part of this. We literally downloaded level 2 radar data for 10,000 tornado events over about a 4 or 5 year period. A couple of slow winters helped us in the process, and this is across the entire CONUS. And we use this information to develop some climatological plots. So there's kind of what I think are some neat ways to look at the information that maybe some of you have seen it, and if you haven't, hopefully this will be a good chance for you to see what kind of stuff we have working in the background. So what we did was we looked at every storm. We took like the old RUC 40 kilometer horizontal grid and said, okay, what was the maximum tornado damage? Every grid, every hour. And then, if there were clusters of tornadoes in the same small area, we just took the highest damage rating. And then we tried to take the mesoanalysis data for that nearest point, and then we looked at what the environments look like, and we also characterize the storms based on their radar signatures. Okay, now the radar can be a mess. Here's just one. Now, it's typical of moving off, especially east of the plains. Whole mess of different convective mode types. I'm not going to quiz you on what was the third storm down from the top, anything like that. The idea here is it can be pretty complicated, trying to figure out what kind of storm produced something. When it's an isolated supercell out here in May, that makes it seem like it's pretty easy, but the reason you remember those cases is because they happen a handful of times. And then, of course, there's other configurations. You can have mishmashes. In this case, some Boeing segment, a supercell ahead of it. This is up in the northern plains. So we basically went through for, I think, a total of 25,000 events, and we looked at this stuff over a multi-year period, and there were several other people involved. If you're really bored, that's a great kind of project to start, but you better be really bored and have a lot of free time. Okay, so what happens when we plot all this stuff? So what I've done here is we've got the tornadoes by convective mode. It's probably going to be hard for you guys to see the scale. The peak there in the light gray, those are two forms of supercells, the discrete and the cluster. So if you ever wonder why, gee, why does everyone focus on May? Well, this is 9 to 10 years of independent information with a strong peak. So that's, those are many hundreds of supercell tornadoes associated with cluster or discrete right-moving storms. And then down in the lower part of the curve, that little dashed line at the bottom that peaks in June, those are the disorganized or so-called landspouts. They were storms that didn't have supercell structure. And then in between, we have some of the other QLCS and the thicker dashed. They also tend to peak a little earlier in the spring. But again, there's a very sharp peak, April, May, and June, for supercell tornadoes. I mean, you guys know this, but this is independent information confirming that. Now, if you look at it in a relative frequency sense, and I know this plot's, it's the same color, these subtle shades of gray. In this case, the supercells are at the top, the solid black and the solid gray. The frequency of supercell tornadoes seems to be relatively consistent. 25 to 40% of all the tornado reports during the course of the year are associated with discrete or cluster supercells. In other words, chaseable type storms. The difference is in the summer, the QLCS events die off and the disorganized storms they get to where they're almost as frequent as the supercell tornadoes as we get toward August. So if you're dealing with, like in my case, forecasting for the whole country, almost half of the tornadoes are not with organized storm types as you get late into the summer. There's not as many of them, but they're with different storm types. So it's not as easy just saying, oh, well, there's a tornado, you should have a tornado watch. You have to think about everything that implies. And if you remember back when we talked about tornadoes, what do we need? We need surface-based convection and some kind of swirly on an almost unobservable scale. That's the entire summer everywhere, almost everywhere in the CONUS. It would be ridiculous. You would just say, well, there's a towering cumulus cloud, there could be a tornado. Nobody would pay attention to you after the first 5 minutes. Okay, so the neat thing about developing a sample like this, we can look at where are the tornadoes most common. This one, we've scaled it to within 40 kilometers where you are. So this is, kind of the same sort of definition that we have for our outlook probabilities. This is the number of times a tornado should be close to you per decade. So you can see the peak is actually down there in northern Mississippi, Alabama. Now this is influenced by the super outbreak back in 2011. It's in this sample. But there's a corridor that extends back into Kansas and Oklahoma. And again, these are just any F-scale rating, just all tornadoes thrown together. And you can see it's anywhere from 5 to 6 or 7 events. So it's every 2 years, 1 to 2 years, you could expect a tornado somewhere reasonably close by. That's sort of the peak frequency. And we can break that down because we had storm mode with it. So in this case, everyone's probable favorite is the upper left. Those are the discrete supercells that produce tornadoes. So you can see there, Kansas-Oklahoma border, it's roughly 2 per decade close to any one spot. And so they're fairly common. Cluster supercells with tornadoes are a little bit further east. And then you notice all the QLCS stuff down in the bottom right. That tends to be more Mississippi, Ohio Valley. So the plains don't seem to have as many quasi-linear convective systems that produce tornadoes, but there are always exceptions. If anyone that looks back at the Moore case, that actually had some QLCS characteristics. I know it wasn't a classic squall line, but if you look at the tornado genesis, it spun up in much the same way that you see these mesovortices. So it wasn't really a classic mesocyclonic tornado. All right, we can combine these, and what I'll eventually get to here, I think it's on the next slide, you'll see essentially why everyone chases in the plains. I mean, it's not only can you see, but you notice the supercell tornadoes tend to be favored Gulf Coast and then arcing up into the plains. The linear stuff in the upper right, that tends to be Mississippi Valley, Ohio Valley. And then when we change these to relative frequencies, the supercells tend to be, each individual type is as high as 40% of the total. So looking at like in the southern high plains, more than 40% of all the tornadoes are with discrete supercells. Look over in the Midwest and you say it's 30% of all the tornadoes are with linear systems. So there's a distinctly different climatology going on here. Anyone who looks at this regularly would eventually figure this out. And then when you combine it all, if you look at the, if you take the cluster supercells and discrete, Western Oklahoma is kind of the bullseye. More than 80% of all the tornadoes are with supercells, Western Oklahoma. But look over Indiana, Ohio, even spilling into Illinois. More than 40% of all the tornadoes are some linear mode. So it's a different forecast problem on average. So it tells you that there are different regimes that are dominating in the plains. And a lot of this goes back to our convective mode discussion. What are the associated boundaries in the Midwest? They tend to be cold fronts, that sort of thing. The orientation of the wind profiles, it favors a linear convective mode. The plains, we tend to have a north-south dry line because of the orientation of the terrain, and it's because westerly flow over the terrain, as we talked. That by itself favors more discrete storms. So the geography and background climatology, you can explain relatively quickly why more linear modes are favored further east compared to out here. All right, and then we can break this down even by season. So there's a whole bunch of ways we can slice and dice this. The upper left is the spring. There's your central plains, Kansas, Oklahoma. Those are the tornadic supercells are far more common there than anywhere else except down into Mississippi and Alabama. And that you can see the northward shift in the summer to the northern plains, and then it collapses back down to the Gulf Coast. So those are just the supercell tornadoes. So you can see the seasonal oscillation of those. And QLCS, just for fun, they tend to be dominating the spring, and it's mostly Mississippi Valley, Ohio Valley region. Though there's some tendency in the winter to see them down in the southern states. All right, with this, we can also look at the ingredients, and that's probably more, climatology is not gonna help you much forecasting. You're gonna say, well, gee, 40% of the tornadoes occur with this kind of storm. That doesn't mean anything on any given day. It just is your background idea. However, what can mean something is, where do my ingredients fall within the distribution? Is, when you're talking about, boy, this is really big CAPE today, what are you comparing that to? Your experience? Well, if you've looked at 2 soundings, that doesn't mean much. If you're aware of 50,000 tornado events, then that means something distinctly different. So the advantage here is that we were stupid and looked at 10,000 of them, so you don't have to. And you can just look at the plots and you don't have to memorize all this stuff. And that's part of the reason I did it, is because there's no way I could even keep up with it. So what I want to do is show you the components of like the significant tornado parameter. And we'll look at those in the ML CAPE. And this is more of the fixed layer version, the 0 to 6 fixed wind difference, the 0 to 1 SRH, and the LCL height, and then the significant tornado parameter. We use the fixed layer version because we had an archive. We didn't have stuff like the effective helicity going back 10 full years. We only had that for like 6 or 7. So to keep the sample size as big as possible, we used the simpler version of it. All right, now I'm going to show several of these box and whisker plots. I want to make sure everybody's clear what we have. What's in the gray boxes in the background, these are the supercell tornadoes. So these are some kind of supercell storm. These are by season, so on the left you have the winter season, and winter is December, January, February. Then we have March, April, May for spring. June, July, and August is what we considered summer, and then September, October, November would be fall. So things to remember in this, our version of summer includes June, which up north is more of a spring month. September, which is lumped into the fall, is actually tropical cyclone tornado season. So there are some different synoptic regimes that may be involved here. But so if you see anything that might make you question it, keep in mind if it's anywhere close to those transitions, it might not be as representative. If we regroup the months, it might make things look a little different. So again, these box, and again, we're showing the 10th to the 90th percentile. The bottom whisker is the 10th, the top is the 90th, and the box, literally half of all the cases fall within the box. So Okay, these are the supercells. You notice this is ML CAPE. It's lowest in the winter. Maybe 500 to 1,000 ML CAPE is pretty typical for the tornado events. And if you see those numbers in parentheses, if you can read them, those are the number of cases. So the supercell tornadoes, it's 127. So there's not that many of them when you look across to the spring, which is roughly 5 times that sample size. And then after the comma, that's the sample size for the QLCS tornadoes, which I will show as the overlay. So again, they're going to have the same format on these box and whisker plots. The background gray plot would be the supercells. The one in the foreground with the see-through black outline, that's the QLCS tornadoes. So one thing that, a lot of this we've talked, the good discriminators. What's a strong discriminator between tornadic and non-tornadic storms? Most people immediately jump to the vertical shear profile, and statistically that works. But if you look at this, let's just look at the difference there with the winter. Look at the ML CAPE. There's not that much overlap in those distributions. The meat of the QLCS tornadoes occur with very small ML CAPE, and the supercell tornadoes are much above that. Look at the other seasons, there's more overlap in the distributions. They occupy more of the same parameter space. Buoyancy is actually, when it's weak, it's a better discriminator than the shear terms are, because the shear's strong all the time in the winter. The strong baroclinic waves, it's nothing to have a strong wind profile. All right, so let's look at the LCL heights. Now you notice there are also seasonal variations in this. So, when we do some gross distribution, everything lumped together, you do have to realize that the ingredients themselves vary seasonally, which really means there are regional variations because of what time of year the events occur. So the LCL heights, you notice this, most of them, they're not extremely high. It tends to be a little higher in the summer, but most of those are under 1,300 meters, so they're not exceptionally high. So the majority of the tornadoes are in the part of the parameter space you'd expect. And again, there's far more in the spring, and that's pretty typical, 1,000 or lower. LCL with the QLCS events, there's virtually no meaningful difference between them. It's the same kind of relative humidity or cloud-based type environments. They're pretty similar. All you see is the seasonal trend where it gets warmer in the summer. Okay, so we look at the effective, or this would be the 0 to 6 year, the standard one. We see the inverse trend. In the summer, the tornadoes tend to be associated with a little bit weaker shear, but again, there's a lot fewer of them compared to spring. So the spring tornadoes are much more common. And remember, also the thing I didn't emphasize here is we're talking significant tornadoes. So these are EF2 plus supercell tornadoes. So these are all significant tornadoes. Except QLCS, we use DF1 plus because there's just not enough significant tornadoes that are linear in nature. The sample was just too small to do any seasonal distribution, so we jumped down to EF1. At least we're confident that it was an actual tornado because there was measurable damage produced by it. Okay, when we overlay this one, you notice in the winter, the bulk shear is actually stronger with the QLCS tornado, so it's weaker buoyancy, stronger deep layer shear. That trend actually reverses as you go into the warmer parts of the year where actually the vertical shear through the deep layer is different. So what it might be telling you is there's a different type of linear system. You think of the summertime linear systems are perhaps more driven by outflow, whereas the winter ones, there's weak buoyancy, but it's very strongly forced. So there's a different nature to the squall lines, whereas you get into summer, they're more driven by cold pools and strong outflow. Okay, so we've got the 0 to 1 kilometer SRH. Now this is kind of interesting. You notice that in this case for the supercell tornadoes, the shear is no stronger in the winter than it is for the spring. But the CAPE was quite a bit bigger in the spring. So we'll see that when we put this all together in the composite parameter. Seasonally, as you would expect, the shear is weaker in the summer. It's a less baroclinic environment. We're deeper into warm sectors. The overall temperature gradient's weaker, so the vertical shear should be weaker. And same sort of thing holds true with the QLCS tornadoes. Again, the winter, they tend to be stronger shear, and it tends to reverse to slightly weaker shear as you get toward the summer. But again, there's a lot of overlap in the distribution, so there's not any good discriminating characteristics. So the point here is that a lot, other than some subtle differences in buoyancy or what forces convective mode, there may not be clear differences between, is this a QLCS environment or a supercell tornado environment? And then we throw it together with the significant tornado parameter. really the only thing that stands out with this is, okay, most of the time the sigtors are occurring with values of 1 or more at the nearest grid point. But there's a much bigger and deeper distribution for the spring. That clearly dominates the significant tornado climatology. There's more in the spring than all 3 seasons combined. And they're much different looking environments when you lump the vertical shear and the buoyancy together. The spring has the second largest buoyancy overall and equally strong vertical shear to the cool season. So it's essentially a case where the spring may not have the strongest shear or the largest CAPE, lowest LCL heights or anything, but there's no significant weakness seasonally. So the spring is the most common time to put all the ingredients together without serious weakness. And one of the places where it tends to happen is right here, late April, early May. So, all right. Now when we talk about, remember, that's all the whole country lumped together. So we do some seasonal stuff. Well, the point is, are there a bunch of significant tornadoes here, like Texas in July? I mean, can anyone remember a single one? I'm sure there'd been one. But point is, the tornadoes tend to be way up to the north in July or the summer, whereas they're sitting down in the southern plains mid to late spring. So we know there's spatial variability in those previous plots, but we haven't really fished it out. So what we can do is that we've got enough of a sample where we can plot a lot of these things and see what they look like. So we're going to do the same ingredients. Now we're going to do a spatial plot. It's kind of an oddball way to look at it, but it's spatial plots of the box and whisker. So we're going to plot like the top whisker, the bottom whisker, and then the middle of the box, the median value. So we'll have those 3 values plotted on here. So I'll give you a minute to orient yourself. On the right would be the right-moving supercell tornadoes. Again, these are all tornado cases. On the left are QLCS tornadoes. And again, think at the top, I kind of inverted this the way it's plotted, but the 10th is the bottom whisker, the 50th is the median, somewhere in the box, and then the 90th would be the top whisker. So in this case, bigger is better. So you notice that the variation, if you compare left to right, that's the difference at the same part of the distribution, how the CAPE varies between the QLCS and the supercell tornadoes. So when we talk about like a high-end CAPE value, if you look there, say in the plains, notice the largest CAPE values with tornadic supercells it looks like the bullseyes near Sioux Falls or somewhere. I think that's on the order of 4,500 to 5,000. So that is large ML CAPE. And then you go down here, it's in the 3,500 to 4,000 range. So actually tomorrow, our forecast is to be in the range of the upper end of the distribution for CAPE for all seasons for anywhere around here in the central southern Great Plains. So the neat thing about a plot like this is you can see where are the storms CAPE driven. Notice the Great Plains stand out. There's that whole axis of 3,000 plus, and then as you move over toward the Mississippi Valley and the East Coast, the values drop off into the, say, 1,000 to 1,500 range is much more common. And then you look on the low end, there's almost always at least 500 CAPE out in the plains with tornado events. Whereas QLCS, it doesn't even register. The values get pretty low. I think that the lowest contour might actually be 100. Okay, so there are clear spatial variations. So literally, Alabama, Mississippi, it doesn't tend to be as buoyant as you would see out here. But as you can imagine, there are other things that compensate, and we'll get to that. So you can sort of look at this. QLCS tornadoes are not very common. If you don't see any shading in the high end of this, that just means there aren't very many events, is what happens. So focusing on the plains, QLCS tornadoes just aren't that common right where the supercell tornadoes were maximized. Okay, so the LCL heights, there's some other things that show up here. Notice it tends to be a little moister environment, just slightly moister overall. That orange gets into the 1,500 range, I believe, and the red would be 2,000. So the red would be about where the significant tornado parameter collapses to 0. That's where that term would zero out everything, which is you just don't find significant tornadoes. And again, these are all the tornadoes lumped together, not just sigtors. Now if you focus out here, so the LCL heights get pretty high, and what do you think most of those tornadoes are in the high plains? At the relatively high LCL heights, but you're still getting tornado reports. Do you think these are long track violent tornadoes or dirt whirlies? They're little dust whirlies, most of them. So we don't necessarily have, this isn't something that contradicts the background climatology. It doesn't say, oh, well, moisture doesn't matter because you can get tornadoes. These are generally weak, and anything that anyone reports that makes it into storm data could potentially be in this database and goofing things up. All right, now we start looking at the vertical shear. This one is the 10th percentile. Those are actually low-end supercell shear values. So what it says is for both QLCS and supercell tornado events, since deep layer shear is one of the strongest discriminators between supercell and non-supercell storms, it just says that it's everywhere. That you don't see a lot of tornadoes with organized convective systems when the vertical shear is weak. You just don't. So even in the low end of the distribution, it's still a supercell type wind profile. And then of course on the high end, the values are in the 60, 70, 80 knot range. So it's very strong vertical shear. And I would encourage you guys download the PowerPoint, or you can go to the Electronic Journal of Severe Storms, and you can for free look at this on ejssm.org. Has all the graphics, so you can look at them at your leisure, because we can't spend as much time as you might want to on this. And then we throw in the 0 to 1 SRH. This is where some of the compensation starts to show up. If you notice the deeper reds and oranges, which are several hundred SRH in that lowest kilometer, tend to be skewed east of the plains. So the plains have the largest CAPE. The strongest low-level shear is out over the southeast in the Tennessee Valley. So, but the buoyancy is weaker over there. So LCL heights are relatively low. So you can start to see how climatologically different ingredients are contributing in a different fashion. The plain storms are more CAPE-driven. The southeast storms are a little bit more shear-driven. But the point is you can get the same outcome with different combinations of ingredients. And so when we throw the significant tornado parameter in there, what you expect to see, and again, the 90th percentile, those are the high-end values that's getting in the 8 to the 10 range. I think the real dark might be close to 10. The peak is actually down there near just west of Huntsville, but it's where essentially you get the relatively large buoyancy overlaps the relatively strong shear in a climatological sense. And so the significant tornado capital of the world is the climatology. Think back to those plots where I showed where the SIGTORs in the spring. It's almost the exact same area. So what this says is that the environment is related to these events. We've explained it in a physical sense, and what we're doing is say climatologically, we can show you where the tornadoes occur with supercells, and we can show background environmental information that backs that up. So it's not an accident that they're occurring from Kansas, Oklahoma down toward northern Mississippi, Alabama, because that's the corridor that tends to get the most favorable environments the most frequently. And again, that's just related to the background synoptic regime. You're close to the moisture source, you're close to the lapse rate source, and you're close to the storm track. It's really that simple. And again, so we just focus there. That's just the overlap. And again, the QLCS events are a little noisier because there are just not that many of them, just enough to contour. And again, just to put these two side by side, again, this is the CAPE and the plains on the top with the 3,000, 4,000 type CAPE environments, whereas the 400 or 500 SRH environments overlap the eastern plains. So you can just eyeball that. If you take the relatively high shear, the relatively large CAPE, it's the eastern half of the Great Plains back down into the Mid-South and northern parts of Dixie. And that's exactly where the majority of the serious tornado outbreaks, long track, really intense tornadoes tend to occur. And even in recent years, you keep seeing that repeat. So the question then is just, this is all just driven by the geography. So what we need to do when we forecast is just figure out how does it fit the geography? How does it fit the climatology? Is this really a high-end environment or not? So, and then you got to think of the details that are going to vary. What sets up this climatology, and how does today vary, or how does it match the background averages that we see? So again, this stuff isn't necessarily going to save you on any one forecast, but it's helpful to know when you're talking about like, wow, this is really strong shear. Most of us don't have enough experience or can't remember enough events to really say that. These sort of plots allow you to not clutter your mind with all those details, and you can go back and actually just look at it and say, okay, I'll let the computer essentially do all that work, bookkeep all this stuff, and I'd say, okay, where does it really fit in the distribution? Is this really a big CAPE day? All right, so we just sort of summarize that stuff. There are clear regional variations in the parameters. Again, we showed that there tend to be higher LCLs in the plains, the western part especially with bigger CAPE and stronger vertical shear to the east. There's a lot of other little details you could milk out of this if you want to look at it. And again, we had a whole paper on this, but it's just interesting to follow this stuff, and I would encourage you to look at it in your, middle of January, nothing's going on. This is neat stuff to play around with for a little while. All right, now I want to look at a few cases where let's apply some actual tornado cases and look at where these environments fall, and I'll show you one of the tools. Hopefully you've seen it on the SPC webpage. And again, I like to mix it up. They're not all plains cases, so we'll look at the Springfield, Massachusetts EF3. There was some neat video from some webcams looking over the river there as the tornado formed. Okay, and this is one that left a ground scar in high-res satellite imagery. You can see that east to west streak of leveled forest is what it is. So that's the tornado damage path. And it starts in Springfield and then continues through the forested areas off to the east. So obviously this was a higher end tornado. And if you leave that sort of ground scarring, again, and they're not necessarily common in southern New England. So this is this is a pretty high-end event for them. But let's look at the environment and let's say, okay, well, what did the environment look like for this tornado event? Our environments are different. How does it compare now that you have some idea what the climatology looks like? Okay, so that morning, just looking at the synoptic wave, this isn't the kind of pattern you would necessarily see in the southern plains with a strong wave, obviously over the Great Lakes, but this sort of synoptic regime with a wave cresting the ridge and moving east-southeastward, that's not a real common pattern for tornadoes out here, but the reason for that is think of what the trajectories look like. If the low level flows more westerly out here, it's coming from a dry source. That's not the case in New England. That may be coming from the upstream moisture source, which is really Gulf of Mexico air that's just come up the Mississippi Valley and around through the Great Lakes. So we have the shortwave trough, and this is just looking at the observed data. It's moving toward New England, so we have height falls. There would be some indication of strengthening gradient, strengthening vertical shear, some source for ascent. Looking at 850, pretty deep low for early June, and then it's more of just an open trough that moves across, but the flow increases. Again, if you just glanced at that, you might say, well, God, the winds aren't backed. If you're forecasting somewhere else, remember, think of what the moisture profiles look like. Where are the sources? A west-southwest wind in Massachusetts is not the same thing as a west-southwest wind in Lubbock. So again, just think of where the air is coming from. So in this case, if you just glanced at it and you get too hung up on pattern recognition, you'd say, oh, the flow's too westerly. There's no way there'd be any tornado. Well, you would have been wrong in that case. Here's the sounding from Albany that morning. In this case, you might think, wow, that's pretty good for that far east. And again, this is early June. We have some relatively steep lapse rates all the way out into New York. Those are conditionally unstable. Some remnant of the elevated mixed layer, and this is a case of very deep low-level moist layer. This is one that would not mix out. If you want tornadoes tomorrow, even better chance, hope that moisture shows up sometime by 12Z, but not banking on it. And then we look over at Buffalo upstream. If you look at the difference, it's not as unstable, but you can already see the influence of the stronger flow. So there's 50 knot flow all the way down to 700 millibars, so we can see the influence of the synoptic system. So there's strengthening flow, and then the question is, what are the details going to look like in southern New England during the day? Okay, so we jump ahead to 18Z. I've highlighted roughly where Springfield, Massachusetts is. And this is one of those, we have the luxury of knowing where it occurred after the fact, so it makes it easier. What's the trough feature there? What is that? Does anyone think is that a cold front? Is it a trough? What is that runs from eastern New York down toward the New Jersey, PA border? Anyone know what that is?
The Appalachian Lee Trough.
Yeah, if you couldn't hear, it's the Lee Trough. It's essentially a weaker Lee Trough. If you remember, we highlighted the Appalachians as kind of a secondary zone for Lee Trough formation. You frequently see these weak troughs. Now again, those mountains are a lot shorter than the Rockies. The response is more subdued, but you frequently see this. Now what's the advantage of a trough-like feature like this? Think of convective mode exercise. What's the orientation of the trough compared to the flow through a deep layer? It's almost perpendicular. So what sort of convective mode would you anticipate just in a general sense with this kind of pattern? Cells or lines? Discrete cells. So we've got a background environment. It's not a plains dry line, but it shares some of the characteristics, and this is somewhat common over there. And notice in this case the dew points, so those are upper 60 dew points, essentially the surface, and then temperatures have warmed up to near or above 80. So they're in the 80s with mid to upper 60 dew points. We plot this as the ML CAPE at 18Z, axis of moderate to strong buoyancy just to the west of them. Now you see the marine influence with the ML CAPE and slightly cooler temperature, or the SYN is hanging on in cooler temperatures. To the east, because again, that ocean, that's cold, deep ocean, it takes a long time to warm that up, and by early June it hasn't happened. LCL heights, modestly low, and when we put this in the vertical shear, we're getting into the supercell range. It's not on the high end, but this is typical of summer or late spring, and then effective SRH is sort of modest, 150 to 200. And again, the pink areas are where the inflow base is actually not at the ground. That's a reflection of that stable air with large convective inhibition right off the ocean surface. And plug this together, the Sigtor parameter, there's a corridor of a 2 or slightly greater just to the west of them. Okay, so we jump ahead 2 hours. Dew points have stayed high. The trough is still to the west. Temperatures have actually warmed up a little bit into the Springfield area. We do have a little bit of inhibition. Now there are some storms around by this point, but it's Cape 2500 or so, which is relatively large for interior southeast New England. LCL heights have stayed modestly low, again, pretty typical of summer. And again, don't worry about seeing the details because I'll show you another version of this. Well within the supercell range for the deep layer vertical shear, and we look even higher, same sort of thing. It's a supercell profile, and effective SRH has actually come up. So either through deepening of the moist layer or strengthening of the lullable flow with the approach of the synoptic wave, we've actually got 200 to 300 plus effective SRH. So if you think back, we're actually getting into where this should look like a pretty reasonable environment for significant tornadoes. And if we look at that again, the Sigtor parameter, that's a 3 or 4, which again, I know you couldn't memorize all the details of the distribution, but a 4 is highly unusual that far northeast. I mean, that's a pretty volatile combination of ingredients, but it does happen. And obviously we got the tornado, but in this case, what I'm emphasizing is the tornado is consistent with the environment. That same environment in Kansas produces the same kind of tornado more often than not. So there's nothing unique necessarily about New England or about Kansas. So the point is when the synoptic regime assembles the ingredients and gives you the right mode of storms, you have to go with the forecast. It does not really matter where it is. Okay, so we'll look at a little bit of the radar just to show you what happened. Now the plains don't often look like this with really close clustering of storms, but this is more common in the east. It's that southwestern storm. And then if we go across, there it is. It's got maybe an odd configuration if you're used to looking out here. But remember, the flows out of the west or west-northwest. So you have to kind of turn your frame of reference a little bit. The inflow region of the supercell is actually off to out of the south or the south-southwest in this case. And that's where the strong updraft is. So it's that southernmost storm in the cluster. And then you see very strong shear couplet with this as it moves through the Springfield, Massachusetts area. And then it gets a little more classic looking as we move to the east. So this is more like what you'd be used to seeing out in the plains. But notice, that's interior southern New England. That looks to me an awful lot like any one of these 3 or 4 more tornadic storms, pick whichever year you want, and then same kind of thing. And again, this is toward the end of the tornado cycle, and that's where, actually you see, if you look close on that map, the background map that we have for GR2, it has the ground scar on there. So you see that light area that goes west from the couplet? That's actually the ground scarring has been preserved for us in the background map. So if you ever want to know where that tornado went, and you can't remember and you happen to be looking at the radar from Boston, there you go. All right, so where did this event fall in the climatological distribution? This is one way to look at it. This is like the poor man's way, is me say, okay, I'll take the box and whisker plot and let's slap these values on. So for summer, the CAPE, I'm just taking the nearest grid values to Springfield. It's kind of in the upper part of the distribution, not quite 75th percentile, but that's respectably large CAPE. And remember, that's the entire CONUS thrown together for SIGTOR. So this is a reasonably high CAPE value for anywhere in the CONUS for a significant tornado event. LCL heights, right there in the middle of the distribution, nothing unusual there, so it's favorably moist. The shear, or again, looking at the, in this case, the ML-SYN is actually a little bit on the high side. So I didn't show this on the other ones, but we'll look at it here. It's slightly higher than you would normally see, but it's not outrageously large. And now going to the vertical shear at this point, it is slightly on the low side for the effective bulk shear, but if you look at that, the arrow points, that's in the 40 to 45 range. So that's still well within the supercell range. It's just a little bit on the low side for a supercell tornado, but if we look at the effective SRH, that's actually getting toward the upper end of the distribution. So the idea is we've got a deep layer shear and buoyancy environment that favors supercells. We have a boundary orientation that would favor more discrete or cluster type storms. It's sufficiently moist and we have pretty strong lullable shear. So we're going to have strong rotation pretty close to the ground, strong pressure perturbations. It's going to draw the air in. It's the kind of setup that goes through that positive feedback for tornado genesis. And when we look at the SIGTOR parameter, that's actually in the upper part of the distribution. So this is a New England event for the season is in the upper part of the distribution, and look at where it is compared to spring. That's like dead on median for spring SIGTORs, which are plains type events. So in interior New England in early June, you had what looked like a just typical plains SIGTOR environment. It doesn't matter where it was. The point is you get that environment and you get the right kind of storms, you get the same kind of outcome. Okay, now, has anyone in here actually used the double-click feature on the mesoanalysis page and ever looked at this? Hey, good, a lot of hands come up. The idea here is that you don't have to memorize all this stuff. Forget all the box and whisker plots that I just showed you. John Hart was kind enough to code this up where these are box and whisker plots just turned sideways. So the whiskers it's just flip it on its side. Typically, those red bars you see, those are what mark the actual values from the nearest grid point where you clicked. Now, again, I didn't have this feature active for the Springfield case. So what I'll do is I'll put those values, I'll just highlight them with the arrows where they fell in the distributions for tornadoes within 120 kilometers of this location. So this is just looking at it regionally. So if we look at this one, we'll just show where the ML CAPE, it's way on the high side for New England. I mean, because if you look at that, it's up almost above the 90th percentile. So this is a way upper end buoyancy profile for them with a tornado. In this case, this should be the effective bulk wind difference dead on. It's right in the middle of the distribution for tornadic storms. LCL height, pretty typical. It's not particularly low, but it's not anything bad. The effective SRH is relatively large. And then when you compare that to the SIGTOR parameter, you notice on this one, the SIGTOR parameter, typically there aren't that many SIGTORs in New England. You notice it's all squished down around 1.5 and less. This is way above the 90th percentile. So for interior southeast New England, this is an outlier environment. It looks typical of the plains, so the idea is let's say you're a local forecaster and you have to deal with this event. You might shrug your shoulders out here and say, okay, it's another SIGTOR day. You know, yeah, whatever, I'll put a hatched area for tornadoes and, don't think anything of it. Whereas if you're saying that in New England, you might go, wow, when was the last time this happened? So some of it might be the local perception as to how common the event is. The other part is just where does it fit meteorologically. What I want to emphasize to you guys is that the meteorology tends to work. Don't get caught up in the hype or the local perception stuff until you've got the meteorology part worked out. So know where you stand, and the same environment produces the same kind of outcome regardless of where you are. All right, we'll jump back out of the plains. I can't neglect the plains for too long, so we'll look at another one. But we won't go Oklahoma, so we'll jump up to South Dakota. They're feeling left out. This will be the Battle case. I know some of you clowns probably saw it. I was hanging out here in Norman, so no such luck. Let's look at that one, and this is pretty classic plains environment, discrete supercell. We've got a strong velocity couplet. And again, we'll look at the environment for this case. So we did the same kind of thing. And look at this. So we've got, in this case, if I just go through the ingredients, and again, a lot of these, it's easier if you just if you can look at them at your leisure. They tend to be in the middle or upper part of the distribution for the case. LCL height's nothing particularly special. And then the SIGTOR parameter up on top, actually for Northeast South Dakota, that's way up there. You know, it's like an 8 or 9 or 10 or something. That's, the main distribution's way off to the left there. So it's an unusual environment even for that part of the plain. So this, again, this is pretty high end. Even if it's only one storm, you can have a pretty bad outcome if it encounters something. And then, you know, we can't leave out the mother lode event. I got to show this one almost every session because this is probably the event of most of your lifetimes. There's not going to be anything too much worse than this one. We'll look at Tuscaloosa, and this one's fun just because it's off the charts in every regard. So tremendous supercell, little debris signature, parent and reflectivity. That one ties for the strongest rotational velocity that we've seen. It ties actually with El Reno at 124 knots. So a delta V of almost 250 knots across that couplet. This is using level 2 data. And we'll put that in perspective here in the last part of the talk. And then when we look at the environment, I mean, this is just fun because it's, you know, everything's on the right side, except for the LCL heights, which are low. Low is good, but everything else is on the right side of the distributions, or at or above the 75th percentile. And those are high-end values for anywhere, anytime. So that's, and this is a case where SIGTORs are common, a place where there's a pretty big sample, and you know that SIGTOR value of 12. Nobody normally sees that. The only places in the world that consistently get that environment are that corridor right back through here. So in this case, you can, if you were looking at this in real time, you'd see the red bars, or sort of pinkish magenta bars on there would actually mark the values for you. So the idea here is it's a nice tool. You don't have to memorize all this stuff, and then you can poke around and see how the environment compares to the climatology within that local region. So you move around and it changes the area, it rebuilds the climo for you. So we've got, essentially this is constructed for every grid point, and it uses all the surrounding ones. So they'll change, and you know, this is how you can really put it in perspective on the more mesoscale sense. And finally, again, I try to emphasize, if the environment shows up, I don't care where it is. Belmont, Arizona, this is near Flagstaff, and this was in the morning. You know, everyone's tornado capital of the world. It's like 12Z at Flagstaff in October. That's just what you think of when you think of SIGTORs. Well, in this case, you see this is an aerial shot with a couple of different tornado damage paths. I think one of the tornadoes came pretty close to the forecast office in Flagstaff. So I imagine that's a morning they won't forget. And looking at the storm, it's the storm, we're looking at the one that's just to the southeast. There's actually 2 rotating storms. Again, this is Arizona up on the rim in the morning, but you have strong rotation with these storms. They are supercells. And then let's look at the environment. Now again, this is Arizona in the morning. You wouldn't expect it to be completely outstanding. First thing you notice, look at the distribution for the tornadoes. Most of them are squished over to the left. Everything where bigger is better, they're kind of mushed to the left because there just aren't that many tornadoes. And most of them are not supercellular. But when you look at this case, so here we have, the buoyancy wasn't particularly large. You know, we're only talking 500 to 1,000 ml CAPE. Again, it was a 12Z case, but it's relatively high for their tornado events. Now we look at the vertical shear. It's above the 75th percentile, so that's strong deep layer shear for any of the tornado events in Arizona. LCL height is way on the low end, which that's one concern there. You're talking desert in general, so moisture is one of your concerns. Then we look at the effective SRH is actually above. It's a high-end value for them. And then when we put that, the fact that the SIGTOR parameter even registers at 12Z is highly unusual for that location. So the point is, it's a low-end SIGTOR environment, but still the potential's there. So if you get caught up too much in the climatology, this doesn't happen here, don't let that sort of thinking override how you should treat the environment. All right, any questions on this stuff? What I want to do is I think next we've got to, if there aren't any, since we're close to the home stretch, you guys can tough it out. We've got maybe 15 minutes left. I think I'll finish on time. I want to look at some relatively newer work we've been doing because we've showed a lot of radar images and a lot of the environment stuff. You know, every time there's a supercell and there's a tornado, everyone, oh, I see a debris ball, I see a debris signature, I see this, I see the tornado. Well, what does the 88D actually tell you about what's going on at the ground? So we'll look at some of that, and we've got a pretty interesting sample of cases here. Okay, so what we've done is, you remember the 10,000 tornadoes? Well, we took a subset of that, and this is like 4,700 of them. All these plotted in here, and you can see the EF scales. So you can see where they were, where it was, you know, it's dominated. Oklahoma, Alabama, Mississippi seemed to be the most common, and so forth, and Kansas. But there's also a fair number in the Ohio Valley also. And the point is, we looked at all these tornadoes, and then we looked at the rotational velocity, which is essentially the peak outbounds, peak inbounds, take the difference, divide by 2, and what does it look like? As close to the ground as we could get for every tornado. So we looked for the max, and then we want to compare the damage ratings to the rotational velocity signatures. Okay, now here's your super box and Wixor plot. There's so many of them. If you focus on the right, the dark boxes, those are the supercell tornadoes. So the right half of the distribution, that's the rotational velocity spread for the EF zeros, 1s, 2s, 3s, and 4+. And then on the y-axis, so remember when I said the Tuscaloosa tornado, 124 knot rotational velocity? That's somewhere off the top of the screen. So it's not, we don't even plot it because there's just no cases like that. That would be above the 90th percentile for EF4+ tornadoes in the lowest cut, and that's at about 3,000 feet above the ground. Whereas if you go to the left, you see the QLCS tornado distribution in the sort of intermediate gray, and then the non-mesocyclonic tornadoes that we have in the sample are in the see-through white boxes. So the point is, you can see that if you look at compare the EF zeros from the QLCS, the disorganized, and the supercell, there are some minor differences between those. The supercells tend to be a little bit stronger. And obviously, the high-end velocity signatures are almost all with the supercells because there's just not that many QLCS tornadoes EF2. So you look at the sample sizes in there, there's only, you know, a few dozen of them with QLCS, whereas there's hundreds and hundreds of them with the supercells. Okay, so just keep that in mind. This is kind of lumping everything together. And we are using, this is just low level. So we're within the lowest 3,000 feet or below 3,000 feet above the radar level. So this is within like 30, 40 miles of the radar. So you're looking like the El Reno storm or something like that. It's about that distance. You're within, say, 40 miles of the RDA. Now, if you go further out, sort of an intermediate distance, you notice the velocity signatures tend to come down a little bit. They start looking a little bit more like one another. There's not quite as much discrimination, but still the violent tornadoes stand out on the right. But if you go far enough out, we start getting out toward like 100 miles out. What happens to the violent tornadoes? Now, the sample gets small. It starts getting harder and harder to tell the difference because you're sampling something higher and higher up in the storm, and the beam is widening, so you're literally not resolving the circulation as well. Now, does anyone think in here that most of these we're actually looking at the tornado itself? We're looking at something that's a little bit larger scale than the tornado, but it's still a pretty sharp reflection. I'm not showing the work here tonight, but there has been some comparisons with small samples of Dow data to 88D. The actual shear couplets are stronger in the Dow data, but there's the same relationship with the 88D. The 88D signatures are weaker, but they show the same tendencies. As the delta V's increase, the damage with the tornadoes tends to increase. Okay, let's sort of throw that all together into this one plot. This is a conditional probability of various EF scales. Now what we've done here is I've just lumped in the gray, those are weak tors. In the green would be strong tornadoes, EF2 or 3, and in the red would be the violent tornadoes. So if you just look at this, and again, these are all tornado cases, so there's no null cases in this plot. These are all tornadoes. So for example, if you're in the 10 to 20 knot rotational velocity range, which is pretty sad, you're way on the left side of the diagram, there's virtually 100% chance that it's a weak tor. If you go all the way over to the other side and you have rotational velocities in the 100 knot plus range, there's virtually no chance it's a weak tornado. even on the scale of what the 88D is resolving. So again, you plot in the 124 knot rotational velocity, which is the top of that rightmost bin. The probability of a violent tornado it's better than 2 out of 3 that you're going. So, and there's a very sharp increase in that 80 to 100 knot rotational velocity range. And again, 80 to 100 knot rotational velocity means there's a delta V of 160 to 200 knots. These are tremendous couplets. You're not going to miss these things, but the point is, to get violent tornadoes and be confident, that's what it has to look like, almost always. So you notice here, where's the transition? If you just want to think in terms of like, wow, I'm looking at GR2 and I see rotational velocity of 65 knots, that's about where a significant tornado becomes more probable than a weak tornado. And I'll show you an unconditional plot that we're still working on that pushes this stuff even further to the right. All right, now this is just another way to look at it, a cumulative frequency plot where what fraction of all the tornadoes occurred. Of course, the top line, the one at 100%, remember these are all tornadoes, so that one's not really meaningful. Of course, they were all EF0 or better through the whole distribution. But if you look at the EF1s, by the time you get to rotational velocity of 90 knots or so on the upper right, virtually all the tornadoes had some measurable damage. They weren't just EF0s. So again, don't worry about memorizing this. You can look back, and I think we have links to some of this on the SPC webpage. Yeah, so, well, and we have the insets, yeah, because we have this built into InSharp. So it's another one of these cases where we try to make the tools helpful. You don't have to memorize it. You can actually plug in the values. And yeah, as Greg mentioned, you can see this in the Python version of Sharp. Okay, so let's look at where some of these cases that I showed you, the 3 radar cases, where did they fall in the distribution? It was rated EF2. This was the Arizona case. So if you look at that, the rotational velocities in the low to mid 50s, that was the peak for the tornado. And so if you follow along that, you would say a violent tornado is highly improbable. I mean, that's what, a couple of % of the cases would be violent at that range. EF3, you're talking around 10% maybe. But EF2, you're starting getting up into maybe a 1 in 3 type chance, and then it's probable that it's a tornado that's stronger than EF1. So the point here is it's in the range of kind of what you would expect. If you just looked at those rotational velocities, you would say the most probable tornado based on this sort of distribution, maybe EF1, and it ends up getting rated EF2. Some of that just depends on what actually gets hit. And I'll have a fun one for you at the end that'll demonstrate that. There's the Bowdle, South Dakota tornado. Its rotational velocity was closer to 70 knots. Again, not extreme. It's rated EF4. Now, the EF4 probability is still relatively low, but that's where you're starting to see the ramp up. EF3 probabilities, again, you're up around 1 in 3, 35%, and it seems probable that there'd be a SIGTOR with that kind. Again, this is just looking at the rotational velocity signature alone. And then Tuscaloosa, it's off the side of the diagram somewhere. EF4, you could argue the only thing surprising there is why was it only EF4? Why wasn't it 5 or 6 or 7 or whatever? Point is, it was clearly a violent tornado. There was an immense amount of EF4 damage, and everything about that storm was consistent with a violent tornado, including the environment. All right, well, here's what, there is a signal in the environment too, not just, the radar data actually is the best discriminator in the short term, but there's a tendency for the probabilities for stronger tornadoes to increase as the environment, as represented by the SIGTOR parameter, gets better. It's weaker. You notice the slope of these is a little shallower, so it doesn't increase as rapidly. And part of the reason is because days like April 27th, there's a tremendous number of strong and violent tornadoes, but there were every bit as the same number of weak tornadoes mixed in with that all count for the same environment. So it does water things down a little bit. So the Arizona case in the SIGTOR parameter falls where you would think it'd be more in the weak TOR type parameter space, but it's not way down on the bottom. There's Bowdle, which happens to hit that little min. That's probably just a quirk in the sample size. And again, the Tuscaloosa is the top of the distribution where the probability of the stronger and violent tornadoes are the highest based on environment alone. All right, so when we look at some of this stuff, here's one where I'm trying to remember if this is the nearest, this must be the remember if this is the point value or the neighborhood one, but anyway, this is just how the environmental ingredients increase. So if you go over to the right, you're getting the stronger supercell tornadoes, and then you've got the weaker disorganized tornadoes there on the left. I believe the box that is see-through is kind of within, I think it's within 80 kilometer range, so kind of what's nearby to the storm, something that you might see in a plan view plot. And the point is, the high-end SIGTORs, 8, 10, 12, you're in the high end of the distribution, tends to show up regionally for a lot of the really big outbreaks that have multiple violent tornadoes. And again, there's a lot of overlap in the environment. Its best discrimination is on the high end. The really high end environments is where the environment seems to make the biggest difference, the really big tornado days. Okay, well, we can combine this stuff into a two-dimensional parameter space where, and this is courtesy of Patrick Marsh, he was an OU grad and he works at SPC. We combine the probabilities and we're combining the influence of the radar signatures with the environment itself, and you notice the increase is most rapid as you go to the right. That's a reflection of increasing rotational velocity, the probability of a significant tornado occurring. But notice there is slope as you go up. If you take the same rotational velocity and SIGTOR parameter increases, the probability of a higher end tornado increases. So it sort of slopes, it's about a 3-to-1 slope. The radar is probably 3 times more influential than the environment would be, but the environment still has some impact. Okay, here's where the Arizona EF2, when you combine the environment with the radar, which gives you the best discrimination, the probability of a significant tornado is in the, we're talking close to 40% range, something like that. So it's a reasonable probability, and for them, that's probably through the roof. They'd almost always be sitting over in the dark blue or wouldn't even be bothering with it. The Bowdle, South Dakota EF4, the probability there, that's getting up into the 70 to 80% range. We're talking for a significant tornado, so this is something that could be of impact. I mean, think about that. You're saying if I know this environment and this radar signature, I could say that a significant tornado is highly likely. And then, of course, the Alabama, the EF4, that one's as high as our probability distribution goes, up close to 90%. It's as certain as you can get. And here's when I said something about an unconditional probability plot, I apologize, this one's pretty noisy. That background dashes, that's one you've already seen, the cumulative probabilities. The important thing here is if you notice that top curve that goes from the upper left and kind of dives down as you get down towards 70, those are the null cases. These are storms. We did the rotational velocity with circulations that did not have tornadoes with them. Now, it's kind of tricky to find all these things. But the point is, if you look around 55 knot rotational velocity, almost dead center in the diagram, that's the first point where the probability of a tornado exceeds the probability of a null event. So 50 to 60 knot rotational velocity is where tornadoes start to become probable compared to a null event. So if you want to think about like tornado false alarms, think about this next time you're looking at radar and you see somebody just carpet bombing tornado warnings, and they're doing it and the rotational velocity is 30 or 40 knots on the signatures. Where is it in this? You're virtually guaranteeing high false alarm by doing that, because the null cases, like at 30 to 39, the probability of a null is 85%. Does anyone know what the false alarm is on tornado warnings nationally for the Weather Service? 75. Okay, it's pretty close. It bounces around in the 72 to 76 range. If you look at that on this plot, that means if you, on average, warn somewhere in the 30 to 40 knot rotational velocity range, you would come up with a false alarm that looks about like 75%. That's what's happening. Now, anyone, have any of you heard of the impact-based warnings? The stuff, Central Region started it and it's spreading to the whole Weather Service. Well, part of the reason we're working on this stuff is that we can, help give some guidance on, what kind of event is occurring now. Now, what's the weakness of a technique like this? Does this tell me anything about what it's going to look like 20 minutes from now? This is a snapshot. All we're saying is what do we think is happening right now? Is that the same as saying, I know what the rotational velocity signature environment will look like 20 minutes from now? Or imagine a 60-minute lead time tornado warning. Good luck. That's all I can say. But you have to be able to diagnose the environment and what's happening before you have any hope of being able to predict it. So it's a pretty ambitious goal to try to forecast these high impact events with lead time, but you can see from this, just what you guys have seen and what you know on your own, there's clearly a trade-off. With lead time comes much greater uncertainty. The average tornado life cycle is much shorter than the warning times. So, you know, if you're starting to get 2 and 3 occlusion cycles ahead of what's actually happening now, I don't think you're going to have much luck. So what this says is something like warn on forecast is going to be extremely challenging to do it with great precision. But you got to start somewhere, and we're going to continue to build on this sample and come up hopefully with at least some way to calibrate where we stand now. Yeah, Greg?
You looked at this sample with respect to tornado path time?
In this case, these are just the peaks anytime during the tornado. So if it's a long track tornado like Tuscaloosa, that might be 8 or 10 volume scans or 12 of them. Most of these, it's just 3 or 4 volume scans. So we're talking maybe 20-minute window. But we haven't specifically compared the peak rotational velocity to the peak damage because there's so much variability in what the tornadoes hit. That depends way more on what actually is encountered. So,
I was just thinking about lifetime.
yeah, so this is during the lifetime. So since the peak damage is anytime during the lifetime, this is the peak rotational velocity anytime during the life cycle of the tornado. All right. That brings us to this. If you're going to try to detect tornadoes with the 88D, I figured I'd be remiss if we didn't at least talk about this a little bit. Maybe you'll get a chance to use this tonight you go home or tomorrow. You know, hopefully it's not anything too bad. But what I want to do is just show an event and to make sure that you have a chance to be consistent, because you see, again, all the time people just love to jump to conclusions. They see a little bit of reflectivity, oh, that has to be a debris ball. This is a tornado. I'm seeing, it's like, look, there are multiple fields, and if you have access to level 2 data, dual pole, there are 3 or 4 things you need to look at the same time before you make any of these crazy assertions. So the idea here is from the conditional probabilities. First of all, if you say that there's a tornado, there's virtually no chance until you start getting into the 40 to 50 knot rotational velocity range. So first of all, let's start with a rotational couplet. Now there's and if you really want, as I've highlighted in red, the higher EF2 probabilities, you need stronger, deeper circulations, typically much, much stronger, very obvious. Now, you know, in terms of the dual polarization radar data, the correlation coefficient, I'll show you on GR2 which ones these are. We won't go into the details. The idea is if the particles that are, you know, we're bouncing radiation off and electromagnetic wave and some energy comes back, if they're all oriented in a similar way, like a consistent type of precipitation, the correlation coefficients are the particles are aligned vertically or horizontally, it's going to be a high correlation because they all look similar. What does tornado debris look like? Stuff going every which way, all sorts of irregular shapes. There's no consistency to it, so the correlation coefficients drop off dramatically. So there should be low correlation coefficients, coincident, not just in the vicinity, but coincident with strong velocity couplets. There's also the ZDR. You can have some minimal signatures there. I'm not going to go into it in great detail. I'll just show you an example of what it looks like. And again, the debris ball stuff means nothing in the absence of the correlation coefficient, usually a little donut hole, and the strong velocity signature. So if you're making a claim that this shows a tornado, and you're not looking at all of these data sources, you know, you're probably misleading yourself. And again, so you've got to look at that combined with the environment. How probable is it to even get a tornado in the first place? And if you start looking at a lot of radar data, you'll find it's actually a lot more difficult than you might think. Okay, so we're going to look at one. This is the Louisville, Mississippi tornado. This was April 28th of last year, high-risk day, Mr. Cohen. One of our esteemed guests here. His first high risk, so we can congratulate him on that one. That was, so here's a case where we have some people might mention, oh, the debris signature. Well, there's a little bit of enhanced reflectivity. They're actually is a little bit there, right? Louisville is kind of circled. So there's a little bit higher reflectivity, but it's not the classic reflectivity ball structure. Very strong velocity couplet, coincident with that feature. We go to the correlation coefficient, and you notice here's the min. You've got to have the right enhancement curves on this. But in this case, those are low correlation coefficients, coincident with the strong velocity couplet and that reflectivity signature. And then even if you look in the ZDR, there are low values, which should also be related to a tornado debris signature. So the point here is that you notice in this case, now this tornado was rated EF4, but if you want high confidence that it's a tornado, all these things are going to be coincident. So usually if you see just one of them or just bits and pieces, that may not mean you have a tornado going on. Okay, so we're going to wrap it up here, and fortunately I won't run too late. We're going to do a comparison case and show you how easy it is to figure out what the F-scale damage rating is in real time. Here's one case, and again, you guys may recognize some of this stuff. This was the evening of April 14th of 2012. This is up near the Kansas-Oklahoma border. The observed sounding from Lamont, reasonably large sector value, deep moist layer, strong vertical shear, steep mid-level lapse rates, moderate CAPE. This is a pretty typical sector environment. Here's another one. This is a Norman sounding. This is a special sounding 17Z. This is the Morday from 2013. So it's, again, steep lapse rates, rich lullable moisture. Vertical shear is not quite as strong, and thus the sector parameter is a little lower at this time. Now, the tornado was a little later, so this is a couple hours earlier. Okay, so we go to the mesoanalysis. The environment had improved on the mesoscale, so we have moderately large values here in central Oklahoma. That's right on. There was also a surface boundary present that the storm seemed to be interacting with. And then we go to the April 14th, or 1Z on the 15th, high-end sector parameter, combined variables. They're still weak inhibition, so it had in the vicinity, the sector parameter of 12. So that's a high-end value. So we're talking top-of-the-line type environment. Okay, here's the Moore storm. There's, a lot of people, again, they jump immediately. Oh, there's the debris ball. Well, in this case, it actually probably was. But because everything else is consistent. Here's the storm up on the Kansas-Oklahoma border. Debris ball, look at it. And again, there's nice tight couplets. So these two storms, in terms of structure, look pretty similar. And they're both, the radar is about the same distance. So they're only looking at like less than 1,000 feet off the ground there where the little tornado signature is. Okay, here's the velocity signature. This is the Kansas-Oklahoma border case. So we just highlight the actual values. It's at 1,000 feet off the ground. Peak rotational velocity, 91.8 knots. So roughly 92 knots. If you remember from the distribution, that's getting into the range where you start thinking violent tornado. And again, that's a very tight couplet. That's like a quarter mile across, peak-to-peak velocity. Very obvious shear couplet.
Are you looking at base velocity here?
We're base storm relative, so this is the lowest cut with the storm relative velocity. Okay, let's go to the Moore case. Lo and behold, the peak rotational velocity is identical to the other one. It's within 100 feet in terms of elevation. So it's almost the exact same distance, elevation, rotational velocity. Most of the metrics of the couplet all look the same. The environment on the other one actually even looks better than this one. Okay, let's look at them. There's our correlation coefficient weakness. There's the little hole you see that's coincident with the strong velocity signature. Same thing with the Moore tornado. Again, this little donut type hole that you'll see, it's a reflection of lofted debris. So what happens in terms of the EF scale ratings? The storm environment, you're both pretty high end. The Harper County one, or right there on the Oklahoma-Kansas border, was a little higher end. Radar characteristics are, these are high-end rotational velocity signatures, high probabilities of a sector, and they all have consistent reflectivity and correlation coefficient signatures that confirm this probably is a tornado producing some sort of damage and lofting debris. The outcome is 4 EF scale difference between the two events. Now, why might that be the case? What's the biggest difference between these two tornadoes?
One hit something, the other
The other one, it's a wheat field versus more. Before they built more up, you guys weren't here probably far enough back, there used to just be a field and it could have been rated the same way. But you have to know what the tornado's encountering. Even the people who did the surveys were surprised. This was a pretty big tornado and it's an obvious signature. Now that one, you don't see that kind of stuff in the east very often because you have trees and more even distribution of population. You know, there's not as much just wide open country as we have in the plains. So the question here is that I would encourage you to think about is, do you downplay an event like that because you think it's in a field? Or do you go with the meteorology and say, I'll live with the fact that it might be an underrated tornado? I'd argue the meteorology should win out because you don't know most of the details unless it's sitting in the middle of the Bronx, and you know that, or it's literally in the White Sands or over the Great Salt Lake, one of the salt flats out there, Bonneville Flats. Unless you know something like that, you don't really know what's going to be in the path of it. You don't know who's maybe driving through or just a few farmsteads that could be devastated by something like this. All right, well, I didn't run too long. I appreciate everyone's patience this evening. Next week, as promised, and I have to do it, we'll go to the dark side and look at the numerical model stuff because I know everyone jumps to that. I'm hoping at this point, at least I've gotten you a little bit fired up about looking at observed data, try to piece it together so that you can develop some sort of conceptual model and anticipate what the numerical models might show, because it gives you a lot better chance to judge the quality of the forecast. And the difference between every forecaster on Facebook or whatever and the good meteorologist is being able to synthesize the observed data. Anybody can look at a UH track. I can see a supercell-shaped thing in a simulated reflectivity. I mean, I can teach almost anyone over about the age of 5 to do that at some point. But to know whether it should look like that and what the likely outcomes are, something totally different. So again, we'll try to have that ready, and if the weather permits, we'll do it again next Tuesday at 7:30. And with that, I guess we'll wrap it up. Appreciate everyone coming and not everyone running off, so it's better than talking to an empty room. So anyway, thanks for coming, and that's all I have for this week. We'll do it again same time next week.